My aim is to talk about a small portion of this vast subject called logic, so that it would enable you to understand mathematics better. Now, so far we have studied propositions. Today we are going to study something called predicates. Now, before we study predicates, I want you to look at this set of propositions. Now, look at this collection of propositions. Now, this collection has three different propositions. First one is all integers are also real numbers. Second one is 1729 is an integer. Third one is 1729 is a real number. Now, I know that we haven't studied arguments yet, but I'm pretty sure that you would recognize this collection as an argument. Why? Because this is trying to tell us that 1729 got to be a real number based on two facts. All integers are also real numbers and 1729 is an integer. Now, by looking at this argument, we have the gut feeling that this is a good argument. It's a very logical argument. It's not a dumb argument like I am the senior most, so I should be the one who would be getting the promotion. It's not an argument like that. It seems like this is a very logical argument. But how are we going to prove that? In order to prove that this argument is a very logically valid argument, we need to find a connection between these three different propositions. Now, the second and the third propositions are talking about 1729. But the first proposition, it says nothing about 1729. It's talking about the set of all integers. Now, how are we going to find a connection between the first and the second and the third propositions? Now, that is where logic involving predicates comes to help. So, now we are going to see what a predicate is. Look at these three statements. Now, the first one says x is a prime number. We know that the prime number is a positive integer which is greater than 1, which is only divisible by number 1 and that integer itself. So, x is a prime number. Second one says y is a goat. Third one says x squared plus y squared is equal to z squared. Now, are they propositions? No. Why? We don't know what x, y and z are. So, without knowing what x, y and z are, we cannot assign a truth value to these statements. But we make these statements in everyday life, right? So, we call such statements predicates. We call such statements predicates. Now, if you look carefully, you would see that a predicate has two components. A variable or variables in this case. In this case it has three variables. In these two cases it has only one variable, and a property. And a property. In the first statement, in the first predicate, the property is being a prime number. The second predicate, the property is being a goat. In the third predicate, the property is x squared plus y squared equals z squared. So, as you can see, a predicate is composed of two components, a variable or variables and a property that these variable or variables are said to possess. Okay? Traditionally, to depict a predicate, we use an uppercase letter such as P, Q or R that represents the property, together with a lowercase letter such as X, Y, Z that represent the variable. Okay? So, in the first case, we can depict this statement as P of X. The second one as P of y. P of y means the property of y. So this one we can say P of x, y and z. The first one as P of x, second one as P of y, third one as P, x, y and z. So instead of P you can use Q here or R here, it doesn't matter. Okay. So how can we convert a predicate to a proposition? How can this acquire a truth value? There are two ways. There are two ways to convert a predicate to a proposition. Now, the simplest way to convert a predicate to a proposition is to replace its variable or variables with known values. With known values. Now, let's say that P of x represents x is a prime number. Okay. If we replace x with 7, P of 7 is a prime number, which is a true proposition. 7 is a prime number. What if we replace x with 57? Now somebody, a very famous mathematician once said that 57 is a prime number without thinking too much, but 57 is not a prime number because 57 is divisible by 3, right? When 57 is divided by 3, there is no remainder. Okay, so 57 is not a prime number, therefore this is a false proposition. Okay, so the easiest way to convert a predicate to a proposition is to replace its variable or the variables with known values. Now think of this one. P of x, y, z is such that x squared plus y squared equals z squared. If we can replace x, y and z with Pythagorean triples, we would always get a true proposition. What is a Pythagorean triple? Let x be 3, y be 4 and z be 5. Then 3 squared plus 4 squared is equal to 5 squared. This is a true proposition. If we replace x with 2, this is going to be a false proposition. So you see, the easiest way to convert a predicate to a proposition is to replace all of its variables with a known value. Now we are going to look at a new term. Let there be this predicate P of x, okay, and think of all the possible values that can replace x that would make this predicate a true proposition. The entire collection of such values is called the truth set of this predicate P of x. Okay, we will look at an example now. Let P of x be x is an even number. Now we know that any even number that replaces x would make this a true proposition. Let's say if we replace it with 4, then P of 4 stands for 4 is an even number, which is a true proposition. Okay, so here the entire set or the entire collection of even numbers is the truth set of this predicate. Now what if we say the predicate is x is an even number that is greater than 100. Now, is 98 going to be in the truth set of this predicate? No. Why? Though 98 is an even number, it is less than 100. So 98 would not be included in this predicate. So in this case, when the predicate is x is an even number greater than 100, the truth set is going to be all the even numbers which are greater than 100. Now I hope you understand the concept of the truth set. Okay. Now assume that this is a known fact. Only the first year math students of campus A are eligible for scholarships. Okay. Now imagine that there is this campus called campus A, right? Now campus A has so many departments: a department of mathematics, department of sociology, department of biology, whatever, right? Of all the students, only the first year students of the department of mathematics are eligible for scholarships. Think that this is true. This is a known fact. Okay. Now consider this predicate. P of x is such that x is eligible for scholarship. Okay. Okay. X is eligible for a scholarship. That is the predicate. Okay. So now in the first method, if the students A, B, C and D are first year students of the maths department, if we replace x with A or B or C or D, then this would become a true proposition, because A, B, C and D are first year maths students of campus A. Okay. That is the way of converting this P of x to a proposition using the first method. Now we are going to look at the second method. So we forget about this A, B, C, D. We don't know any of these students in the maths department. Now we are going to make a statement. Not only one statement, lot of statements. Now look at these 5 statements. Now our predicate is this: P of x such that x is eligible for a scholarship. That is the predicate. Now we have 5 statements. All students of campus A are eligible. Now has it got a truth value? Yes. Are all students of campus A eligible? No. Only the first year math students are eligible. So this is false. It is therefore it's a proposition. It has become a proposition. Some students of campus A are eligible. It is true. Why? The first year math students are students of campus A, right? So some students of campus A are eligible. It is true. Therefore it is also a proposition. Third one, all students of maths department are eligible. False. Only the first year students are eligible. Some students of the maths department are eligible. True. The first year students again. Some students of the sociology department are eligible. False. False. So now we have constructed 5 propositions from this predicate. We have constructed 5 different propositions from this predicate. Now if you look carefully, you can see that all these propositions, the property is visible. Being eligible, this is the property. This is the property. Now instead of talking about a specific person or a specific value, now in this case a specific person, what was done is to apply this property over a specific group, a well-defined group of students. Here, all students of campus A, some students of campus A, all students of the maths department, some students of the maths department, here some students of the department of sociology. So this property is said to hold over this well-defined group of students. We are not talking about a specific person here. So now this well-defined group seems to be constructed by a larger group, students of campus A here, students of campus A here again, students of the maths department, students of the maths department and students of the sociology department. And then it is kind of bound by these words here, all, some, all, some. Now this bigger collection from which this more well-defined collection is constructed is called the universe of discourse. Universe of discourse. So in the first proposition, the universe of discourse is students of campus A, right? In the second, again the students of campus A. In the third, students of the maths department. In the fourth, students of maths department. In the fifth, students of the sociology department. So that is the universe of discourse. What we do is, using the two words all or some, we have kind of bound the individuals in this universe of discourse to a certain extent. When we use all, we are concerned of all the individuals in this universe of discourse. When you are saying some, we talk about some individuals of this universe of discourse. That would create a proposition, right? I hope you understand this. Now this is the second way of converting a predicate to a proposition. Now the truth value of such a proposition that is created from a predicate depends on two factors. What are these two factors? The first one is the universe of discourse. We are given the free will to choose the universe of discourse. Here we have chosen campus A, here the Department of Mathematics, and here the Department of Sociology. Because we chose the Department of Sociology, even if we use some or all, this would be false, right? So it is important to select a proper and appropriate universe of discourse. The other fact is using all or some. In the third one, even if we have properly chosen the correct universe of discourse to make it a true proposition, because we have used all here, this becomes a false proposition. Okay? In order to make it a correct proposition, it has to be some students of maths department. Okay? Now we know how a predicate can be converted to a proposition using the second method. Now we are trying to show this using logic symbols. For this, we need three new symbols. So the first one is this symbol, which is somewhat similar to the uppercase letter A being flipped 180 degrees vertically. Okay? So we call this the universal quantifier. Universal quantifier. This symbol stands for all or any. Because when we say any student in this class is a Christian, which means that all the students in this class are Christians, right? So they mean the same thing. So this symbol stands for all or any, and it is called the universal quantifier because it talks about everybody in the universe of discourse. Okay? Now there is this other symbol which is somewhat like the uppercase letter E being flipped 180 degrees horizontally. Now this is called existential quantifier. Now this stands for, or this represents, there is or there exists. Okay, there is or there exists. That's what it means. Okay. Now, it is not a controversial thing to use the word all in mathematics, because when we say all the elements in the universe of discourse have some property, it means everybody has that property. There is no controversy. But we cannot use terms like sum when it comes to mathematics. In day-to-day life we use sum all the time, but we can't use the word sum when it comes to mathematics. So we have introduced this, there is or there exists. It's another way of saying sum, a more appropriate, more concrete or logical way of saying sum. Now what we are saying is, there is somebody in this group, right? Okay, instead of saying some elements in this group, what we are saying is there is an element in this group. Okay, so we have, this is what we use instead of sum when it comes to logic. Okay, now the third symbol is the membership symbol, symbol of membership, which means belongs to, or is a member, or is an element, right? So these are the three symbols that we need to know. Now we are going to show you how to represent a predicate that was converted to a proposition using these three symbols. Okay, now let D be the set of even numbers. Okay, D is the set of, capital D or the uppercase letter D represents the set of even numbers. So imagine the property P is a prime number, okay. D is a set of even numbers, property is being a prime number, that is the property. So when we say there is an x which belongs to D, P of x, that means there is an even number which is a prime number. There is an even number which is a prime number. Okay, this is a true proposition. Why? Number 2 is an even number and it is the only prime number which is an even number. Okay, so this is true. Now if we say all x in D, P of x, this is false because all even numbers are not prime numbers. Okay, now we are going to study the quantifiers a bit more. Okay, now consider this proposition. This is not a predicate, this is a proposition now. Okay, what we are saying is all x in D have this property. Okay, now assume that this universe of discourse, we are going to list all the elements in this universe of discourse. Let D equals all these elements, x1, x2, x3, x4, the number of elements may be finite or even infinite. Okay. Now here, now this x does not have a subscript. The reason is this x could be any of these ones. Okay, so that is what it means. It means all the x in D, right? So these are the x's in D, x1, x2, x3, x4. These are known values, right? These are known values. So now this, what this means is, now try to understand it very carefully. For this to be true, for this to be true, for this to be a true proposition, I repeat, for this to be true, then P of x1 and P of x2 and P of x3 and P of x4 and this must be true for all the x's in D. This is what it means. Okay, so we can say that this is equivalent to this statement. This is equivalent to this statement. Okay, so this is what it means. For this to be true, all of this must be true. So you know that for a conjunction to be true, all this got to be true. That is why we have used the conjunction. P of x1 must be true, P of x2 must be true, P of x3 must be so. Everything, all the elements must have this property for this to be true. This is what it means. Okay. Now consider the existential quantifier. Now we know that this is a proposition. Okay. Now we are saying that there is an x in D who has this property. Okay, we are saying that there is an x in D who has this property. Now this, when we say this, for this to be true, then P of x1 or P of x2 or P of x3, can you see we are using the disjunction instead of the conjunction, right? Or P of x4 or it is applied for all the other elements. Okay, so this is what it means. This is equivalent to this, right? If in the case of the universal quantifier, all of this got to be true. All elements must have this property. Here, if a single element has this property, that is enough for this statement to be true, right? Okay. Consider this proposition involving the universal quantifier. Okay. Now, if somebody makes this statement where D and P can be anything, right? How are we going to prove that person is wrong? Okay, it's something like, let's say all the even numbers are prime numbers. That is the statement. This represents all the even numbers are prime numbers. Somebody says that in a gathering. Now you are there. How you are going to prove that it is false? Do you have to prove that all the even numbers are not prime numbers? Or if you can have just one even number which is not a prime number, that alone is enough. You don't have to say that all the even numbers are not prime numbers, which is actually false, right? Because 2 is a prime number. Okay, so instead of saying that, right, even let's say assume that it is true, instead of saying that, it is always enough to say that if one element in D does not have this property, then this cannot be true, because here we are talking about all the elements. Now we are going to prove that. We know that all x in D P of x is equivalent to px1 and px2 and px3 continue. Okay. Now can you remember De Morgan equivalence? The first equivalence says, let's say that these are, now here we are talking about propositions, so we use lowercase letters p and q. These are two statements, right? This is a statement. Here we have, what we have is the uppercase p. Now this is not a predicate, this is a statement, because here we are using a known value. Okay. Now here what they say is the negation of the conjunction of two propositions is equivalent to the disjunction of the negation of the first proposition and the second proposition. This is what it means. We can easily prove this, though I am not going to do it here. This is true for any number of conjunctions, right? So we can use this here. Therefore, negation of this proposition is the same as negation of this. Okay, negation of this. Now from De Morgan equivalences we know that this is equivalent to negation of p of x1 or negation of p of x2 or negation of p of x3, or this would continue like that. Okay. Now we know previously that this is equivalent to p of x1 or p of x2 or continued, right? So this is equivalent to there is an x in D which is not p of x. So it's the same way as saying there is an element in D which does not agree with this predicate. Okay. So if we want to prove this statement or this proposition is false, all we have to do is we have to prove that there is an element in D which is not p of x. Okay, an element in D which is not p of x. That's what we have to prove. Now we will see how we are going to disprove a statement involving the existential quantifier. Now imagine someone came up with this proposition. How are we going to prove that this proposition is false? Right? If someone says that there is an x in D which agrees with this proposition, then if we can prove that all the elements in this in the universe of discourse do not agree with this proposition, then we can safely say that this is false. So we are going to prove that. Okay. Now we know this is equivalent to P of x1 or P of x2 or continues. Okay, so the negation of this statement is equivalent to negation of this statement. Okay, now from De Morgan equivalences, this is equivalent to negation of px1 and negation of px2 and negation of px3. It continues like that. So this means for all x in D, right, this property does not apply. Okay, that is how we are going to prove. If someone comes with a statement like that, if we are going to prove that that statement is false. Now again, to summarize the entire thing, right, if one comes up with a statement involving the universal quantifier, statement like this, to disprove this we have to prove that there is an x in D which do not agree with this property. The negation of this property is we are saying no to this property, right? So it does not have this property. And on the other hand, when we say that there is a x in D which agrees with this property, to disprove this statement we have to prove that all x in D do not have this property, right? I hope you understand. Now, before we come to the conclusion of this video, I would like to show you certain statements to understand certain concepts better. Now let's say we want to show that all the elements in the universe of discourse, have two properties. One property is P, other property is Q. Okay, so what if we write it like this: all x in D, Px and Qx. Is this correct? The answer is no. Now this means x has property P, this means x has property Q. This means this is not a proposition at all. We have written it like this because we do not know the order of precedence when it comes to the quantifiers. You have to understand that the two logic quantifiers precedes all the logic connectors. What is the precedence of the logic connectors? The negation precedes conjunction, precedes disjunction, precedes unidirectional implication, precedes bidirectional implication. You have to understand that the logic quantifiers precedes all the logic connectors, right? So when you are writing like this, it means we have to first consider this component. We have to consider this component. Okay, if we want to show that all x in D have both the properties, then we have to write it like this: all x in D, right, have these two properties. We have to include this within a parenthesis. Now it makes sense. It is a proposition. It is saying that all x in D have both these properties. Okay, that is one concept. Now sometimes, now the scope of a quantifier, now consider this. When we say all of x in D P of x, it means that this quantifier is talking about, its scope is the entire universe of discourse. When we are writing something like this, we are talking about only one element, right? That is the scope of the quantifier. Okay, that is the kind of the area within the universe of discourse it exerts its power. So we call that the scope of the quantifier, right? Now we will look at this example. All x in D have this property P of x and y. Now there is no mentioning of y here. Y seems to be out of the influence of the quantifier. Let D be the set of even numbers. Okay. Now instead of allowing y to be free, now we are going to bind y using a quantifier. Okay. So we say all x in D, there is a y in D, Px and y, P of x and y. Okay. Now let the property be x squared equals y. Then we are saying when any even number is squared, the result is another even number, right? That's what it means. For all x in D, there is a y in D such that P of x and y. Okay, when any number is even number is squared, the result would be another even number. Okay, so when we use such quantifiers, right, whose scope overlap like this, we call these quantifiers nested quantifiers. Nested quantifiers. Okay. Now mind you, this does not necessarily have to be the same universe of discourse. This could be anything, any universe of discourse. Okay, that would still make it a proposition. Now in this video we studied about predicates, and then how to depict a predicate, then how to convert a predicate to a proposition by replacing the variable with a known value, and then we found out how to convert a predicate to a proposition by using a set of well defined or bound collection of values. Okay, and then we found out about how to using logic symbols, how to express this process of quantification, right? And then we talked about the universe of discourse, the truth set, and finally the scope and about nested quantifiers. Now you'd be wondering, do we really need this stuff? These propositions, the predicates, this quantifier, that quantifier, right? All these symbols. Well, you do. If you want to understand the true beauty of mathematics, if you want to understand some of the most interesting areas of mathematics, like the set theory or even real analysis, you really need this ideology. Without this, you won't be able to proceed. Sometimes, or most of the time, when you want to see something really wonderful, right, something so majestic, you often have to travel through very difficult, right, 4x4 roads, right, but the final result is really amazing, right, it's really beautiful, right. So imagine that this is something like this. So try to understand these concepts, okay, try to understand these concepts, then you would see the true beauty of mathematics. With that, I come to the conclusion of this video. Thank you for watching.